Good morning to all of you. Welcome back to Hospitality Engineering. Today we continue Energy Conservation and Energy Efficiency Module 12. Case Study 1: Energy Efficiency using Speed Control. Topics to be covered in this video. Identify main motor starting methods. Recognize the frequency converter principle and its advantages. Realize substantial energy savings using speed control. Reduce harmonic distortion generated by frequency converters. Calculate the payback of an investment in a variable speed drive. Let us see in detail. Many motors only have two settings, on and off. They operate at a constant speed. If a motor turns at constant speed drives a device or process to produce less output. Adjustments are required to achieve the desired output level. This adjustment is often achieved by letting the motor run at full speed while using downstream devices to block part of the output. For fan applications, we have motors generating a full flow of air, and we use dampers to partially block and reduce the flow. For pump applications, we have motors generating a full flow of fluid, and we use dampers to partially block and reduce the flow. Energy is used to generate the output and then it is immediately thrown away. To begin with, let's see how damaging speed control can be financially. You need to know a few simple physical laws in order to do this. These are called the affinity laws. Flow is the output from a device such as a fan, pump or compressor, expressed in cubic meters per second, or cubic feet per minute. It is proportional to the shaft speed of the motor. This means that with half the shaft speed, you get half the flow. Pressure is proportional to the shaft speed, squared. So with half the shaft speed, you get a quarter of the pressure. Let's say you were getting a pressure of 100 for a shaft speed of 10. For this example, the units of pressure or speed don't matter. 10 squared is 100. Now let's reduce the shaft speed to 5. 5 squared is 25. Half the shaft speed, quarter the pressure. Now is where it gets interesting for us. Power is proportional to the shaft speed, cubed. Half the shaft speed uses 1/8 of the power. Let's see that calculation. Imagine you have a shaft speed of 10. 10 cubed is 1000, 10 times 10 times 10. Now let's take that speed down to 5. 5 cubed is 125. 5 times 5 times 5. Half the shaft speed, 1/8 of the power. So, if you have a fan or a pump that doesn't need to run at 100% flow or pressure output, you can reduce the shaft speed, and hence the power consumed by the fan. This is an example of an ideal curve of power compared to flow, based directly on the affinity law. Note that real devices will have curves that are offset or a different shape because real devices are not ideal and have varying performance characteristics. Even a small reduction in speed can result in a significant reduction in power consumption. A variable speed drive is more efficient, but there are a number of other benefits to consider. For instance, with variable speed drives, starting and stopping operations can be smooth and perfectly controlled. Slow starting also minimizes the inrush currents that often accompany a motor suddenly starting. Inrush. Currents cause voltage sags that can have damaging effects on the motor and other affected equipment. Variable speed drives are sometimes called variable frequency drives. This is because the drive receives AC power at a constant frequency, such as 50 or 60 Hz, and converts it into a variable frequency for supply to the motor. They are found in many applications such as elevators, HVAC systems, pumps, fans, cranes, and conveyors. Let's look at the question of how you start the motor. There are three options associated with starting a motor. They are direct online, star, and delta or soft starting. Direct online starting connects the motor stator windings directly to the mains supply. The motor will start and accelerate according to its natural characteristics. This starting method is suitable for stable supplies, mechanically stiff and well-designed shaft systems, and it is the most common starting method available on the market. The starting equipment consists of a main contactor, effectively an on or off switch which is suitable for the required current, and a thermal or electronic overload relay. The disadvantage of a direct online starter is the high inrush current that occurs when the motor starts turning. It may draw a current that is 5 to 7 times the nominal current until it is up to full speed. These inrush currents can generate mechanical shocks that warrant oversized wiring and additional surge protection. Next is the star and delta starting method. This method needs 3 contactors and a control part to manage the contactor sequence. Both ends of the motor windings must be accessible. Motor windings are connected in star formation upon starting. Once the motor torque matches the load torque, the winding connection is changed to delta connection. Star and delta provides a softer start than direct online, but acceleration is still not controlled. Star and delta is always used for motors above 10 kilowatts to preserve and optimize the electric installation and mechanical parts. The motor is started with the Y star connection and accelerated as far as possible, then switched to D delta connection. Notice how the star and delta connection causes a starting current of about 1/3 the current associated with direct online starting. This rupture in the star and delta starting current is the result of the starting current making the switch between star and delta. Although this starting method is softer, it requires a motor with 2 extremities of wirings connected to the terminals for a mains 380 V, 660 V, star/380 V, delta. When starting in star, the motor nominal voltage, the peak of current, and the starting torque are divided by 3. Soft starters are used instead of star and delta for levels over 10 kilowatts. Soft starters increase voltage gradually to generate a smooth, steady acceleration, and are perfectly compatible with direct online and star and delta motors. Although a soft starter does smoothly and gently start a motor and bring it up to full speed in a controlled manner, it does not provide substantial energy savings or variable speed control. During the starting process, the soft starter progressively increases the motor voltage so that the motor becomes strong enough to accelerate the load to rated speed without causing torque or current peaks. Soft starters can also be used to control the stopping of a process and provide thermal and short-circuit protection for the motor. Let's first look at mechanical variable speed drives. The basic concept behind adjustable sheave drives is very similar to the gear-changing arrangement used on many modern bicycles. The speed is varied by adjusting the ratio of the diameter of the drive pulley to the driven pulley. Historically, electrical VSDs, even DC drives, were complex and expensive and were only used for the most important or difficult applications. So mechanical devices were developed for insertion between a fixed-speed electric drive motor and the shaft of the driven machine. Mechanical variable speed drives are still favored by many engineers, mainly mechanical engineers, for some applications mainly because of simplicity and low cost. But they are not very efficient and reliable, and the speed range is very limited. Hydraulic VSDs are often favored for conveyor drive applications because of their inherent soft starting capability. In hydraulic systems, the motor or the coupling is managed by oil pressure rather than a magnetic field. It is this pressure regulation and flow control that allows for progressive starting and speed control. Hydraulic drives also tend to be more efficient than electrical ones in systems that require high torque in a small space. They are used in all types of transportation and earth-moving equipment because of their inherently high starting torque. Both of the common types work on the same basic principle where the prime mover, such as a fixed-speed electric motor or a diesel/petrol engine, drives a hydraulic pump to transfer fluid to a hydraulic motor. The output speed can be adjusted by controlling the fluid flow rate or pressure. The electromagnetic or eddy current coupling is one of the oldest and simplest of the electrically controlled variable speed drives and has been used in industrial applications for over 50 years. In a similar arrangement to hydraulic couplings, eddy current couplings are usually mounted directly onto the flange of a standard squirrel cage induction motor between the motor and the driven load. Using the principles of electromagnetic induction, torque is transferred from a rotating drum, mounted onto the shaft of a fixed-speed electric motor, across the air gap to an output drum and shaft, which is coupled to the driven load. The speed of the output shaft depends on the slip between the input and output drums, which is controlled by the magnetic field strength. The Ward-Leonard system comprises a fixed-speed three-phase AC induction motor driving a separately excited DC generator that, in turn, feeds a variable voltage to a shunt-wound DC motor. So, this is essentially a DC variable speed drive, a complex structure that has largely been replaced by electronic devices. Since the 1970s, the controlled DC voltage required for DC motor speed control has been more easily produced from the three-phase AC supply using a static power electronic AC or DC converter, or sometimes called a controlled rectifier. Because of its low cost and low maintenance, this type of system has completely superseded the Ward-Leonard system. However, DC motors are less common now due to technology and maintenance cost. DC motor drives. In the case of an AC to AC frequency converter, the mains AC supply voltage is converted into a DC voltage and current through a rectifier. The DC voltage and current are filtered to smooth out the peaks before being fed into an inverter, where they are converted into a variable AC voltage and frequency. The motor supply is controlled so that the ratio between voltage and frequency remains constant. This allows an AC motor to provide its rated torque up to its rated speed. The variable speed drive is also known as a frequency converter and is known for having very accurate speed and torque regulation. It has a rectifier bridge followed by an inverter. Both allow voltage amplitude and frequency to be varied. Step 1. The input rectifier converts the three-phase network supply to DC. Step 2. The DC voltage that is obtained is then filtered. Step 3. From this DC supply, an inverter rebuilds an AC supply to feed the motor. Here we see a table comparing different starting methods. As you can see, variable speed drives not only yield better performance, but have lower operating costs as well. Variable speed control has many advantages compared to older technologies. Let's very briefly look at these advantages and some of their applications. Bottle conveyor. For a bottle conveyor, the aim is to not break the bottles when the conveyor starts or stops. A speed drive here will allow for soft customized speed ramps in order to accelerate and decelerate the conveyor without shaking the bottles. Load controller. Load control is important in large installations, but so are peak current and mechanical shock limitations. Variable speed drives allow electrical and mechanical equipment to be downsized by limiting the starting current. Lift control panel. For passenger lifts, movements must not be abrupt and perfect positioning is required independent of load. A variable speed drive is the most suitable solution to control speed and positioning. The variable speed drive also ensures braking control, which is synchronized to the movement. An escalator, with frequent starts and stops, tends to stress mechanics. An electronic speed drive ensures acceleration and deceleration while limiting jerks that can accompany high torque applications. VSDs feature a user interface for monitoring, diagnostics, and control. An LCD screen and pull-down menu replace the old buttons and potentiometers. Drives are also communicating devices. They can be managed by a controller using one of the many Fields bus protocols available on the market. Speed control can also contribute to energy savings. For pump and fan installations, this savings can be upwards of 70%. The red line is the power versus airflow curve when the airflow is controlled with a damper. For 80% airflow, the motor is operating at almost 100% of its power. If the damper is replaced by a variable speed drive, airflow information is used to adjust the motor to the right speed. When the fan speed varies, power increases proportionally to the square of airflow. For 80% airflow, the motor operates at only 50% of its power. This means power consumption is halved by the use of a variable speed drive compared to a damper solution. How is energy wasted in water distribution? Let's look at an example. In a distribution system, water is moved by a pump. In this simplified irrigation installation, the pump is powered directly by an AC supply and always runs at full speed, whatever the demand. A valve opens and closes to vary the flow. Reducing the flow using a valve causes what are called load losses. As the valve slows the flow of water, a large part of the power is lost. Providing 80% of the flow causes the pump to consume 80% of the power. Providing 50% of the flow causes the pump to consume 65% of the power. Remember the affinity laws we saw at the beginning of this course? Power is proportional to shaft speed, cubed. Although this is an irrigation example, the same principle applies to other pumping systems. How can we save up to 50% of the energy in water distribution? Let's replace the direct-on line, starting with a variable speed drive. The valve is no longer needed since the flow can now be adjusted by variable speed control of the pump. To vary the flow, the speed reference is adjusted. The difference between the green curve and the red curve represents the energy savings. Providing 80% of the flow, the pump only consumes 50% of the power rather than 80%. Providing 50% of the flow, the pump only consumes 20% of the power rather than 65%. In this video, we have demonstrated energy efficiency using speed control, which will have one more part to conclude it. I would like you to stay with me through the rest of this series. Like and share this video and subscribe to our channel for more training modules. Thank you for watching.